Hello everyone, I am Shreya. Today, let's discuss the research paper on missing value imputation titled as Review and Analysis of Literature from 2006 to 2017. So basically, this research paper aims to analyze 111 different journal papers published between 2006 and 2017 from the perspective of experimental design. We will discuss about missing rates, missing mechanisms, statistical and machine learning based techniques for missing value imputation, evaluation methods, and lastly, missing data simulation strategies. Technical issues regarding MVI are: first one, the experimental dataset could either be complete or having missing data. Second, during imputation process, we divide the dataset into complete and missing dataset. The complete dataset is used for estimation, which could be done by statistical as well as machine learning ways. Third, performance evaluation. One method is that we assess the differences between real and estimated values. In the other one, we perform data mining. As we can see in this setup, we first take an experimental dataset and then remove some values to make it incomplete. Now, we divide it into two sets of complete and missing data. We perform imputation methods on complete data and use this for predicting the missing values. And finally, we have a complete dataset. Now, we evaluate its performance and repeat all the steps again. Here, we have a distribution of number of datasets of each domain from 2006 to 2017. We can observe that the datasets of University of California and of medical domain are dominant compared to other domains like software and finance. Moving on, we have missing rates. Generally, the missing rates of most of the datasets were less than 30% or between 30 to 50%. Very less datasets had missing rate greater than 50%. Now, we have missingness mechanisms. There are three different types of missingness mechanisms. They are MCAR, MAR and NMAR. MCAR occurs when the probability of an instance having a missing value for an attribute does not depend on either the known values or the missing data. MAR occurs when the probability of an instance having a missing value for an attribute may depend on the value of that attribute. In other words, when the distribution of an instance having missing values for an attribute depends on the observed data but does not depend on the missing data. NMAR occurs when the probability of an instance having a missing data for an attribute may depend on the value of that attribute. This figure shows the number of works detailing simulations of different missingness mechanisms. As we can see, MCAR and MCAR plus MAR have the highest proportion. Moving on, we have techniques of imputation. First, statistical techniques. In the first one, in main, we compute missing data by average of the observed data, and in mode, we compute missing data by mode. Second, EM algorithm. In this approach, we have two steps. First, we calculate expectation from the observed data, and next, we update parameters by maximum likelihood. Third, we perform a linear regression. And lastly, least square method, where we produce final result by replacing the least square. In this distribution of usage of different techniques across many years, we see that mean mode method and EM method are widely used. Now, let's talk about machine learning based techniques. Clustering. Each cluster is the mean of objects in the same cluster. To compute missing values, the distance between incomplete data and identified cluster centroids is calculated. KNN or kth nearest neighbors. In this, the nearest neighbors can be identified by Euclidean distance. Missing data is used as testing case in which the complete and missing attributes represent input features and output features. Decision tree. In decision tree, each internal node denotes a test of an attribute and each branch represents an outcome of the result. Leaf nodes represent classes. Uppermost node in a tree is the root node with the highest entropy. Random forest. About random forest, multiple decision trees are constructed based on bootstrapping procedure and the final predictions are given by average values. From the year-wise distribution, it is evident that KNN is mostly preferred compared to other techniques. Moving on to evaluation methods. In the direct method for discrete values, we compute performance by this formula. PCP stands for percentage of correct predictions. which is given by 100 into number of correct predictions by total number of predictions. On the other hand, for continuous values, we compute mean absolute percentage error and root mean square error given by these formulas. The second evaluation method is classification accuracy, where we use different classifiers such as ANN or naive Bayes and test their performance. From the graph, we see that there is a strong inclination towards the use of direct method as compared to use of classifiers. This graph shows the number of works using 10 different classifiers. We observe that decision tree and KNN have been preferred the most. Now the last topic, missing data simulation strategies for missing value imputation. Concisely speaking, we have different strategies to perform missing data simulation. First one is to directly use the whole of the chosen dataset by making it incomplete with a specified missing rate. The second strategy is to divide chosen dataset to training and testing subset by cross-validation, and either of the subset is used to perform missing data simulation. This distribution shows that the first strategy is more widely used than the other. Very less proportion of the studies have used cross-validation method. Conclusion. After reviewing the entire research paper, what we can conclude is that MVI for incomplete datasets is very important in data mining, so that final results of mining is not affected. We have successfully analyzed the missing rates, missingness mechanisms, the statistical and machine learning based techniques, evaluation metrics, as well as missing data simulation across 111 different research papers.
So hello everyone, my name is Deven Pratap Singh and today I am going to explain you guys our topic missing value imputation using deep learning. So let us start the video. So first of all, what is time series data? It refers to data points collected over time at regular intervals. It's widely used in various real-life applications like monitoring and forecasting. However, missing values are common, ranging from 5% to even 90% due to various factors like sensor issues or signal loss. These missing values can negatively impact tasks like classification, regression, and forecasting. Traditional methods often overlook the temporal aspects of time series data. Deep learning techniques like RNN, GRU, and GAN show promises in filling these missing values by capturing hidden temporal patterns. Recent research has applied these deep learning methods to impute the missing values in multivariable time series data. So, this is the concise overview of major approaches to time series imputation, and we have categorized existing methods based on the underlying principle and techniques. So, first of all, deletion method. Deletion method includes removing observations with missing values from the data. This is suitable when missing values are minimal and won't impact downstream tasks. However, when missing value rates exceed about 5%, this approach leaves the data incomplete and unsuitable for analysis. Constraint-based method. These use dataset rules like differential dependencies and comparable dependencies, considering both timestamp and value similarities. Petri nets can also be used to impute qualitative event values in time series data. Neighborhood-based methods like KNN or dbScan find missing values by clustering and identifying nearest neighbors based on other attributes. They replace missing values with the mean of these nearby neighbors. Regression-based methods use regression models to predict missing values from the complete attributes, while in time series data, autoregressive models like ARX and ARIMA forecast missing values based on historic data. Advanced techniques like IMR offer both anomaly detection and data repair, relying on historical data and accurate nearest neighbor. Statistical based method. They use models like mean or median imputation and advanced technique like IIM, which adaptively learn models for varying number of neighbors to impute missing values. Unlike regression-based method that relies solely on historical data, these models utilize the entire dataset, including both past and future data, for a more comprehensive understanding of the raw data. Expectation maximization method for missing data imputation involve two stages: the expectation step and the maximization step. They iteratively fill in missing values using statistical model parameters and update these parameters to maximize the likelihood of the distribution of the imputed data. Multi-layer perceptron employ MLP to predict missing values using complete values involving input, hidden, and output layer. MLP learns a function to impute missing values by minimizing the loss function based on input variables. MLP is used to predict missing values in neural network-based diagnosis system. Matrix factorization method aims to impute missing values by decomposing the data matrix into two low-dimensional matrices, extracting features from the original data. This process identifies correlations to fill in missing values similar to classical collaborative filtering techniques. Moving on, we have preliminary, kind of a prerequisite before discussing the methods ahead. In a multivariable time series, we have a timestamp list T denoted by T0, T1, Tn-1, and time series X denoted by xt0, xt1, and xtn-1. The observation xti consists of D attributes denoted by this. So we also have a mask matrix in which if the value is missing, it is 0, and if the value is not missing, it is 1. So we also introduce the concept of time lag to represent the time interval between two adjacent observed values of x, and it is calculated using this formula. So to understand the concept of time lag better, here is an example. So here time series is given and the timestamps are given. We compute the mask matrix from this. If the value is none, the mask matrix is 1, and if the value is observed, it is 0. So now we compute the delta. We can compute using this formula, as everyone can use this formula, but if to know the real concept of time lag, we have to understand it in a conscious way. So first, as you can see, if the in the starting there is no time lag, so every value is 0. Here if the masking is 0, so see here, so the previous value is observed, so we just calculate the time difference. Here the previous value is observed, so we calculate the time difference. Here also the previous value is not observed, but the last value, the most recent value is this, so we calculate the time difference. Here also the previous value is observed, so we calculate the time difference here. So thus all values are 5. Here is the real understanding begins. So listen carefully. Here the mask matrix is 0. Here the previous value is observed, so we calculate the time difference 13 minus 5, which is 8. Here mask matrix is 1, so the value is not observed. So here also the previous value is not observed, so we take the last observed value. So thus we calculate this minus this. So 13 minus 0 is 13, because the last observed value was this. This was not observed, none, this was none. So here the previous value is observed, so 13 minus 5, which is 8. Here the previous value is not observed, but the last previous value, the most recent previous value is observed, so we calculate 13 minus 0, which is 13. So we just calculate the previous recent value, the most recent value, and thus we can calculate the time lag. We can also compute using this formula, but everyone can use this formula. Now the methods which we are going to discuss are GRUD, GRUGAN, E-square-GAN, BRITS, and Naomi. So the first method is GRUD. GRUD is a deep learning model designed for time series imputation, recognizing the strengths of R and N in handling multivariate time series data. It introduced the concept of time lag and replaced missing input variables in the GRU with a combination of existing values and a statistical value. This is the statistical value and this is the existing values, computed using element-wise multiplication with factors m and 1 minus m. This is the mask matrix. This is also the mask matrix. It is the element-wise combination of the existing values and the statistical value. This can be any value, can be mean, median. So an important discovery was that missing variables tend to default to a certain value if their last observation was a long time ago, with the input variable's influence fading over time when data is missing for an extended period. So the decay rate in GRUD is negative exponent of the max of this function. This is the learnable parameter and this is the decay rate, which we observe last. It guarantees that larger the time intervals are, the less their influence on imputing the missing values. We update the input variable by using this formula. Here MJTI is the mask matrix. This is also the mask matrix. This is the last observed value of xj at time tj. This is the last observed value, and this is the value at a time close to ti, thus ti dash. this is close to Ti, not Ti, it is close to Ti. And gamma j x Ti is the decay rate at time Ti of variable xj. X tilde j is a learnable parameter to capture the baseline or default value for variable xj. So this is the model of GRUD, and as you can see, it has hidden decay layer, this, and input decay layer, this. So this is similar to GRU, but it has these two things extra. GRU is similar to GRUD but lacks input decay layer, focusing on capturing time information. GRUGAN utilizes a generative adversarial network, which we are calling as GAN, with a generator and discriminator based on GRU. G aims to generate realistic time series from random noise Z, while D evaluates data authenticity. This approach enhances imputation accuracy, employs a WGAN structure for stability, but faces challenges in converging and maintaining accuracy with random noise inputs, limiting its practicality. So this is the real sample passed to discriminator, which gets trained on it, and then noise is passed to the generator, which random noise is passed to the generator, which alters the real sample, and now the discriminator has to find out if the sample given is real or fake. If it correctly predicts, generator is trained, and if it wrongly predicts, then the discriminator is further trained. So this is the structure of GRUGAN, and here as you can see, GRU lacks input decay layer. It is just similar to GRUD, as you can see it has hidden decay layer, but it does not have an input decay layer. Here it does not have input decay layer. Moving on, we have BRITS. BRITS stands for bidirectional recurrent imputation for time series. It is a pure RNN based approach for time series imputation. BRITS employ a temporal decay factor gamma t, causing hidden states to decay based on recorded time lags. RITS, a previous model, is the unidirectional version of BRITS. BRITS, in contrast, employs bidirectional RNN by training two models in both forward and backward direction. It introduces a consistency loss to consider information from both directions. Bidirectional RNN offer improved performance over unidirectional models, mitigating issues related to bias explosion. So here, as you can see, we update the values in BRITS using this formula. So here x cap t represents the predicted or imputed value. XCT represents the intermediate variable representing a combination of the observed data xt and the imputed value x cap t. So here mt is the mass matrix. Gamma t is the temporal decay factor which we discussed earlier, which is the negative exponent of max of this function and the linear combination of these terms. ht is the hidden state at timestamp t. It is updated based on the previous hidden state ht minus 1, the decayed previous hidden state ht minus 1 dot gamma t, the intermediate value xct, and a sigmoid function sigma. Lt is the loss or objective function at timestamp t. It is a dot product of mass matrix into the loss function, which is generally square loss error xt minus x cap t. So here is the model of BRITS. So as you can see, here is the input layer. This is the complement variable which goes to the recurrent layer, and then it goes to the regression layer which goes to the estimate variable, and then it goes to the complement variable here. As you can see, this x4 goes to here, and then it is again passed similarly this, and this. These are the missing values which are computed using this. So E-square GAN. E-square GAN is a GAN-based model that generates and completes time series data using unique autoencoder structure based on GRU, which captures sequential dependencies. Unlike typical RNN-based GANs, E-square GAN incorporates an autoencoder within a generator, a novel approach in the field. It compresses original time series data into a low-dimensional vector with GRU and then reconstructs a complete time series to deceive the discriminator. The discriminator employs a recursive neural network with an encoder framework. E-square GAN generator is designed as an encoder-decoder RNN to enhance the training stability and accuracy. Experimental results demonstrate that E-square GAN outperforms existing models in the generation and completion of time series data. So as you can see, this is the autoencoder. As you can see, this is the E-square GAN structure. Here the incomplete time series is passed to the discriminator, and here the incomplete time series is passed to the autoencoder, which generating the complete time series x dash, which is then passed to discriminator, and then discriminator has to find out if it is real or fake, and here it is again passed to this. The output is passed to this and discriminator. So discriminator is trained, and the generator, the autoencoder, is also trained. Naomi stands for non-autoregressive multi-resolution imputation. It is a model for imputation tasks that utilizes bidirectional RNN similar to BRITS. It combines forward and backward RNN to create a joint hidden state. Naomi employs a unique prediction approach, divides tasks efficiently, and enhances performance through adversarial training. However, it doesn't consider time gaps because it does not use timestamps when inputting data into RNN model, making it unaware of irregular time series, although they can still be used as input by removing their timestamps directly. So here is the structure of Naomi. In this, we are given x1 and x5, which is passed to the hidden layer h1 and h5 respectively, and then from that hidden state x3 is calculated, which is then passed to h3, and then from h3 and h1 the x2 is calculated, and from h3 and h5 x4 is calculated similarly, which we discussed earlier, the same formula, the same method. So to summarize all this is the similarity between all the structures. As you can see, GRU-GAN builds upon the work of GAN, and E-square GAN is the auto-encoder enhanced GRU-GAN. Both GRUD and BRITS are pure RNN model. BRITS and Naomi both incorporate bidirectional RNN structure. So this is the most important part of the whole lesson. So this is a summary kind of thing. So in this, all the things are related to each other. So these are the characteristics of the models. So GRUD is RNN based model based on GRU. GRU-GAN is hybrid model based on GRU plus GAN. It has adversarial training. E-square GAN is GRU-GAN with autoencoder enhanced as discussed. BRITS is pure RNN with bidirectional nature. Naomi is hybrid with RNN and GAN. So in conclusion, we categorize time series imputation methods into three groups: deletion, tradition, and learning based approaches. We focus on three learning methods: GRUD, GRU-GAN, and E-square GAN, where the latter two incorporate GANs for better imputation accuracy. GRU-GAN builds on GRUD's concept, and E-square GAN further enhances GRU-GAN with an autoencoder achieving state-of-the-art results. These methods have broad implications for various domains due to foundation nature of imputation. Techniques from other fields can also be adopted for time series imputation. In the future, we anticipate improved use of temporal information and more precise method, eliminating the need for overwhelming choices. Ultimately, we aim to make missing data in time series less challenging. So thank you if you watched till the end of the video.
Okay, so if you find this video informative, do give it a like, and thanks for watching.